Ballad of the Beverly Hillbillies played, not even gonna try with the banjo. So y'all know the story, right? So imagine that's playing in the background. So come and listen to a story about the search for gravity. Poor Galileo said, explain how this can be. Then one day he was working in his lab, and up through his mind came a bubble and math. Equations, that is, solutions to the problem. He's dropping different masses to avoid a great disaster. Most folks said, well, the heavier one's going to fall faster. Aristotle said, well, that's the way it's got to be. So he loaded up his stuff and he moved to Italy. Leaning Tower of Pisa, that is, started dropping cannonballs. Well, now it's time to clearly state just what the facts should be. Mass is not a factor when things fall because of gravity. You're all invited back again to Galileo's game, that independent of the mass, they always fall the same. Acceleration, rate of change in velocity. That's what we call it now. So, there's my work in there. If I could play the banjo, that would
Sign
have
Charles's forehead.
What are you trying to suggest, Cohen?
Imagine that, just Stanley Bergkamp when I go play today. Bro, what is that on his head?
No. Okay.
Also on your forehead.
So,
Not the Sharpies.
no, we're not. So, here's what we've dealt with so far, and that's just been kind of one wave by itself. But in reality, waves interact with different things. So this is what's known as an Ames tube, okay? And this is, and you'll see this in contrast with an open-closed system. This is what's called an open-open system. So I've got two different frequencies of tuning fork. This is at 830, and this one is at 883. Okay, so there's not much, and that's the frequency. Okay, so you should be able to at this point determine the wavelength if you know this. So you've got the speed of sound, which you know to be.
We better connect your
Oh,
phone.
Where's the string?
Kind of wait. Wait. You may as well use it.
Bro, I heard that on the video you did.
annoying, isn't it?
I know.
Here, I'll make it lower pitch so it's harder to hear.
I don't know about you, but that sounded
No.
louder.
That did.
Then
That didn't
if
sound
I see
loud.
you,
Hey, guys.
so please.
I mean, this unit's about time.
Harm your fan.
Okay, so this has an 880 frequency tuning fork. So we take 343, somebody do the math, and divide that by 880 meters.
389.
What do you get?
So like 0.39.
0.39 meters. Okay? Now, here's the problem with coming about how we represent sound waves, okay? Sound waves in reality are longitudinal waves, okay? So it's hard to express visually. Cohen, I swear to you, I have a raging headache right now, and I'm going to do that to your head in a second.
Please. Please.
Will help.
So it's hard to represent what that looks like. So even though it isn't technically a transverse wave, a lot of times we'll draw it like that just because it makes the visual easier to see. So when we say that that thing has a wavelength of 0.39 meters, that's what that's referring to. Now, the other one that you've got, that is 883. So what's gonna happen to that wavelength? Because it has a slightly higher frequency of 883, so the wavelength is going to be a little bit smaller, okay? So somebody take 343 and divide that by 883.
0.388.
What'd you get?
0.388.
88. Okay, so not a huge difference. Okay, now you wouldn't think, okay, hey, what's the big deal? It's not that big a deal. So here's what I'm going to do. I'm going to take this and I'm going to make it vibrate. I'm going to hold it up to the end of this. So what's going to happen is that it's going to make that air inside of this column begin to vibrate. Okay, so when I do that. Okay? Notice that gets a lot louder. But when I take it away, it stops. Okay? I'll do this again. It's pretty loud. Take it away, it stops. So that is the 883 one. Now, if I take the 881,
That's actually exactly.
and I do that, it gets louder. But then when I take it away,
It hangs around longer.
that sound is still there. Because what this is doing is that this is matching the exact resonant length, the resonant frequency of the air inside the tube. So once I get that going, it's creating almost like the same idea of the glass. Okay? That glass vibrated with a certain frequency. And when I changed the condition, the glass vibrated with a different value. So the same thing is true of this. So when I hold this up, okay, and I get that vibrating, and I take it away, the air inside of that is still like reinforcing itself and you can still hear it. But if I do it with the 883, as soon as I take it away, it stops. Because it's just off by enough that it doesn't match that frequency. So this is here an open tube. Now in contrast to that, you could have an open closed tube. So Dan, you're gonna have to give this a little bit of a spin.
Okay.
So this is the basis of the lab that you're gonna do on Monday. So all this is a piece of black plastic. Now let's talk buoyancy. What do you know about the two forces right now?
They are
Equal.
balanced.
They're balanced, right? If I push it down and let go,
Goes
He
back
goes up,
it goes back up, okay? If I lift it up and drop it,
he goes down.
it goes down, eventually finds its own point of equilibrium. So here's what I'm gonna do is I'm gonna take this tuning fork and I'm gonna hit it, and I'm gonna hold it over the top of it. So what's gonna happen is that that's going to send a wavelength down, and it's gonna hit the surface of the water, and then it's gonna bounce back up, okay? So if I can find just the right point, it's gonna get really loud, just like that did. Okay, so if I can find that point of resonance. So, come on. Okay? See that point right there? That point where that got loud. So what's happening right there is the same idea as that tube. You're reinforcing that. So what's happening is that it's like it's in phase. So now if you have a completely different tuning fork, where is, so this one's like 349, okay? That was like at 880, this is 349. Much lower frequency. So with a much lower frequency, what do you know about the wavelength? It's gonna be longer. So now if I do this one, okay? So notice that that one was much farther out of the water than the first one was. Now, here's the reason why. When you have what's called an open closed system, and again, we represent it as a transverse wave. In reality, it's not. So, what's happening is that here's this tube, and there's the water, and that sound is bouncing down off of it. So, here's the visual that you have to make. That imagine that you have an entire wavelength, okay? Where you could have something like this. So from here to here would be the entire value of L, okay? So imagine that you could generate a natural standing wave where this whole thing is one wavelength. So how much of that wavelength is right there? Fourth of it, a half of it, an eighth of it, what? A fourth, okay? So this part of this wave is 1/4 of, let's get that up. Oh, come on, change. This is 1/4 of lambda. So what you're gonna do in the lab on Monday, you're gonna measure that point, okay? So that's what you're gonna do. You're gonna hold up these tuning forks. And you're gonna adjust the height of that column until it just reaches that point where it becomes very, very loud. That's gonna represent 1/4 of the wavelength. So then how can you figure out what the entire wavelength is? Multiply by 4, okay? So, if you look at the comparison of what I just did, when I had that really, really low frequency and I had that really, really long wavelength, that tube was quite a ways out of the water because of the fact that that was a relatively long wavelength. When I had that 80 hertz, which was a much higher frequency, what happened to that wavelength? It became much shorter. So that 881, that one was much lower. So it was much closer to the water because of the fact that it had a higher frequency, so it had a shorter wavelength. So that's why that hit that point of resonance at a much shallower depth than the one with the higher, than the one with the lower frequency. Makes sense. Now, the other thing that you get, and I'm going to show you this in just a second, we'll go to the back. When you have a standing wave, and we've done this, but I'll reinforce it. So you have what we call nodes and antinodes. Okay? So nodes are going to be the points where you basically, in effect, don't have any motion at all. Okay? Your antinodes is where you have your maximum movement from the equilibrium point. Now, let's see if we can find like a mathematical model. So, if I have, and I'll show you this in just a second, but I want to kind of lay out the math first. If I have this situation, how many nodes and antinodes do I have? 2 nodes and 1 antinode. So this would have 2 nodes here and here, and one antinode. Okay? God, I cannot spell. That spells antinode. Trust me. Work with me here. That spells antinode. So, if that's the situation, and the distance between these 2 points, let's say, is, I don't know, 3 meters. If that distance between these 2 points, like Preston's gonna hold one end of the spring, I'm gonna hold the other one, and we set this up. If that distance is 3 meters, what's gonna be the wavelength?
6 meters.
6 meters, right? Because this is like half of the wavelength. Cool? Okay. So I had 2 nodes, that was 3 meters. The entire wavelength is 6 meters. Now, if this distance is still 3 meters, and I set up a pattern like this, now how many nodes do you have? 3 nodes, and you have 2 antinodes, okay? And the wavelength here is going to be 3 meters. So, what kind of, can you figure out a mathematical formula? Magic? Well, clearly, as the number of antinodes increases, okay, what happens to the wavelength? What happens as the number of nodes increases? Wavelength gets, wavelength decreases. So for both of them, there's an inverse relationship, right? As the number of antinodes or nodes gets bigger, the wavelength becomes smaller. So what's a simple one on this one? So this distance was 3 meters. There was 2 nodes. What was the wavelength? 6 meters. So in that situation, I could take the gap between the 2 of them and multiply it by the number of nodes, and I would get 6. Now, does that hold with this though?
No.
Why not?
Those are 3 nodes.
I got 3 nodes.
And
So if I followed that same pattern, if this is 3 nodes and this distance is still 3 meters, the wavelength should be 9. Now, what did we say that it was? Was it a direct or inverse relationship?
oh, wait.
So just a straight multiplication isn't going to get us anywhere.
Gotta do some goofy square root stuff, then I don't know. I don't know anything.
That sounds like an excuse not to do the math.
Now,
How about we call it a day?
how about we take the distance, and I'm just going to throw this out here as a possibility.
Oh,
Cohen, shut up.
there's a possibility?
As a
Kindly.
possibility.
There's more than one?
As 1 over the number of nodes. Don't like that?
No.
Why not?
Because we just set that
You're
one
back
as
to-
one. Yeah, the one from before.
Hold that over. Let me go back and show you how it works. Okay, just hold that over.